This is chapter 16, problem 11 about the water skier who is moving at a certain speed on top of the waves, and then she's jumping from one crest to the other. And you can see the algebra here. I actually will look at the algebra here a little later, but I'm already going to use the solution so I can make this animation here realistic. So this one here kind of obviously looks like the water waves, and here we have the crests. This is a physics software that doesn't allow me much graphics opportunity, so this green rectangle here is the water skier, and the water skier is supposed to jump up, land on the next wave as both of the wave and the water skier are moving to the right, and then lands on the next wave, every 0.6 seconds. I'm not going to make this rectangle jump up. It would have been too difficult for me to figure this out in the software here. So she's just moving to the right, and then I'm going to stop it every 0.6 seconds. As I said, I already put the data in here, so the water skier is moving at the given 12 meters per second. The water wave already uses the solution of 1.09 meters per second going to the right, and the wavelength, you can see it here, here's 0, and here's the next crest at roughly 6.5 meters, or the second crest, it is roughly 13 meters, and then roughly 19.5 meters. So that already also uses the actual solution that the wavelength is 6.5 meters, which it is from one crest to the other. Okay, here's the animation, and then I'm going to stop right here. A little bit too late, so 0.7 seconds here, which means that, yeah, it was about 0.6 seconds when she hit the next crest, and right there. Just a little bit too late here. Okay, I think you can see us here, 1.2 seconds here. There we go. Roughly 1.8 seconds after the third crest. Okay, this is actually out of the picture. There, just about 2.4 seconds on the fourth crest, and then the last one here. Right there. Too far. So 3.1 respectively here was 3.0 seconds after the fifth crest. As I said, it became a little tough here to stop that just in time. So every 0.6 seconds. I'm going to turn it around because it says that on the way back she's now going against the waves. Let's see if I get 12 here. Not quite. So there it is, negative 12. Now she's going against the water waves. Yep, just about 0.5. Just about 1 second. 1.5 seconds after the third one. I stopped it too late here, so just beyond 2 seconds here on the fourth one. 2.5 seconds here on the fifth one. So again, that's a frequency of 0.5 seconds, just like the problem says, and 0.6 seconds when she is moving with the waves. So the original or first part of the problem, I'm going to change this back here to plus 12. Okay, so the idea is that she has to complete this distance here from one crest to the next, which is a given wavelength, with her speed. However, at the same time, the wave is moving towards the right. So this crest is not here anymore, okay, but it's a little further to the right. So it's as if you keep the wave stationary, but you make the skier slower. I'm going to try to do this one here. So here she goes. Notice the it's a little bit too late. So the crest already went on, which means that she started jumping here and she had to arrive over here, and her 12 meters per second, it just took her a little longer in order to make that crest. I didn't express that very well. But let me show you the other point of view where I define this one here. It's somewhere here. System, center, system of mass of this one here. I just saw it a moment ago. There we go. And then I'm going to do a new reference frame, which is going to be this wave here. And now, yes, the wave is stationary, and there she goes. So the wave actually didn't move in the screen here. Actually, the coordinate system moved to the left, so it's as if she is slower in order to get there. Again, I didn't express it very well, but notice the time is 0.6 seconds. So the algebra on that one is that she is jumping every 0.6 seconds. That's when she gets to the next crest. And if this was all, that this would be her speed, then it would be just 12 times 0.6 seconds, and that would be the distance she jumped. However, the wave is moving as well, and because she's moving with the wave, it seems like her speed is diminished relative to the wave. So therefore, this one is subtracted. So the wavelength equals this. Subtracted two velocities multiplied by the time. And then when she's going the opposite direction against the waves, oops, there's a mistake here. That's a 0.5 seconds when she goes against the waves. But now she encounters them more frequently. So it's her speed plus the wave speed. So relative to the wave, it seems like actually she's faster encountering those crests. So this one here is the second equation on towards the left. This one is the first equation towards the right. The two wavelengths are of course the same because it's the same waves. And then set them equal, which eliminates the wavelength lambda. Do some algebra, and so the wavelength here, not the wavelength, somebody just knocked on my door, so I have to figure out where I was. So the result is that the only variable left is the velocity. Solve for that with the algebra, and you come up with 1.09 meters per second, which I already used in my animation. And then from that, you can also compute the wavelength itself, which comes out to 6.55 meters. And you notice that both of those work just fine in my animation. And that was Chapter 16, Problem 11, the water skier.